Okay, thank you, Simsek. Oops, is it? Okay. Okay, so it's great to be back here. Okay, yeah, so this talk is completely unrelated to yesterday's talk. It is something I've also been working on. Thank you, sorry, I forgot. Thanks. Something I've also been working on in the last few years in PDE. Right, so many equations, many physical systems in PDE are governed by differential equations called evolution equations. So evolution equations are differential equations, either ordinary differential equations, only involving one variable time, or partial differential equations involving space and time, which involve, but they evolve in time. So they all have to involve time. So these are one of the basic equations of motion in physics. The simplest example, maybe, of evolution equation is the first order ODE, where so partial t of u time derivative of u is f of u. So u is the unknown solution. So this might be maybe the location of the trajectory of some particle, for instance. So for any given time, in some time interval, let's say from 0 to t, your particle takes values in some vector space Rm, maybe 3 dimensions, for instance. And you move around, and your velocity is given by some function of your solution. And so f is given to you, and then you evolve. Okay, so this is a very simple example of an evolution equation. A more realistic example would be this partial differential equation here. It's called the nonlinear wave equation, NOW. So now second order in time. So but u depends on time and space. So u is a function of time and of d spatial variables. For example, d might be 3, for instance. So if you live in 3 dimensions, also taking values in some vector space. So this might be, for example, some electric field, electromagnetic field, or some other field. This is a nonlinear wave equation. You take minus the second time derivative of u plus the spatial Laplacian of u. You take the double space derivative in every direction, add them up, take the Laplacian, and that will be some function of u. Okay, if this was 0, this would be the linear wave equation, and if you put a nonlinear function of u here, this is the nonlinear wave equation. And so f is some function from Rm to Rm, and so this is the nonlinear wave equation. A slight variant is the nonlinear Schrödinger equation. Shows up in various quantum mechanical models. So it's very similar. It's just that your solution, your field now takes values in the complex numbers to the m, rather than the real numbers to the m. And instead of taking double time derivative, which is what would give you the wave equation, you take I times the first time derivative. This will give you the nonlinear Schrödinger equation. So these are several common examples of evolution equations that show up in physics. There's a lot of subtleties as to exactly what these equations mean. If your solution is rough, it has discontinuities or singularities. Ooh. But I'm not going to care about in this talk about these subtleties. I'm always going to consider smooth solutions and solutions which decay in space, finite energy, these sort of things. Okay, and one of my favorite equations, but also one of the most difficult to deal with, is the Navier-Stokes equations, which describe incompressible fluids, or idealized incompressible viscous fluids, such as water. So here, again, the solution is this is a system of equations involving an unknown field u, a function of time and space. This is the velocity field. So at any given point in space and time, the water has some velocity. That's a vector, and that's u of tx. And then there's also a pressure at any given point. At any given point in time and space, there's the water pressure. That's a scalar. And then there's these two equations of motion. So there's the Navier-Stokes equation. This is the continuum version of F equals ma, Newton's laws. So the acceleration, the time derivative of the velocity, differentiated along the velocity field. So you also have to add this transport term here, u dot the gradient of u is equal to negative the gradient of the pressure. That's the force coming from the water pressure, plus a viscosity term, nu times the Laplacian of u. That's the effect of the viscosity of water. It dissipates some of the energy, So nu is just a positive constant. It measures just how viscous your fluid is, and then delta is just Laplacian. But then you also require that U is incompressible. So U has to be divergence free. Okay, so the density of water never changes, at least in an idealized setting. And so this system is the Navier-Stokes equation. Sometimes we consider the case when the viscosity is 0 in viscid fluids, and then those are called the Euler equations when you set nu to 0. Okay, so these are examples of evolution equations that show up in physics, and we study them mathematically. The natural problem we study, so there's several questions you can ask about these equations, but the natural problem to ask usually is the initial value problem. So what you do is that at initial time equals 0, you specify what your solution is doing, and then you ask, if you know what's going on at time 0, you ask what happens at later times. So for example, if you have a body of water and you know right now what the velocity is and pressure is at any given time, any given point in space, can you then predict what happens, an hour from now, a day from now, what happens to the fluid in the future given what happens at time 0? So this is the basic initial value problem. Now, the initial data you specify at time 0 depends a little bit on your equation. So for instance, if you have a first order ODE, like this ODE here, dtu equals f of u, what you do is that you specify just initial position. You just specify what your particle is doing at time 0, and then that tells you what happens at later times. If you had the nonlinear wave equation, this equation here, it turns out you specifying initial position is not enough. It's not enough to know what your wave. So this sort of equation describes, for example, the evolution of some membrane, like the surface of a drum. Well, that's not exactly this equation, but you can think of it as similar. But it's not just the position at initial time which is important. You also need to specify initial velocity. So for second order equations in time, you need both position and velocity specified in order to control the evolution at later times. But NLS, for instance, is first order, you need initial position. Okay, so what data means is a bit different from equation to equation. For the fluid equations, Navier-Stokes and Euler equations, what you specify is the initial velocity only. So there are two unknowns, velocity and pressure. But it turns out that once you are given the velocity, you can actually solve for pressure. You can actually, if you take the divergence of this equation, you can actually solve for the pressure in terms of velocity. So you don't need to specify initial pressure. You just need to specify initial velocity, but it has to be incompressible. It has to be divergence free, so there's a compatibility condition that you specify. But other than that, there's really no constraint. Okay. So. All right, so the field of PDE has been studying evolution equations and the initial value problem for decades. And to oversimplifying quite a bit, what usually happens for these equations is that if you specify the initial data correctly, you usually have local existence. So it's usually not too difficult to establish a local existence result. So given any, say, nice smooth solution with good enough decay, at time 0, given smooth enough data, you can usually solve the equation for a short period of time. There's some short period of time where the fluid is guaranteed to evolve properly without developing any weird singularities, or your wave is not going to blow up on you. But what is usually more difficult and often actually unknown is the global existence problem, whether you can actually solve your equation for all time. And sometimes you can, sometimes you can't. So this is true even with the simplest of evolution equations. For example, this first order ODE, derivative of u equals f of u. So of course, as you learn in your undergraduate PDE class, ODE class, that given any ODE like this with a nice some initial data, u naught and some smooth nonlinearity, there's the existence and uniqueness theorem of Picard, which tells us that you can always solve this equation locally, and so there's always some time, which I call t star, for which you can solve your equation, and you can solve it until some point, and then you stop. Now, sometimes t star is infinite, which means that you can solve the equation all the way indefinitely, but sometimes it's finite, so that you can solve the equation up to some point, and then at that point, the equation can no longer be solved. And furthermore, if your equation can only be solved for a finite amount of time, then there must be a good physical reason for doing so, and the good physical reason is that you have blowup. The solution must actually go to infinity. So so what you can actually prove is that either you have global existence, the time of existence is infinite, or you have finite time of existence and your solution is becoming infinite at that time, which is it is really physically not existing after that time. Okay, so for example, a very simple example, the first example everyone learns is the Riccati equation, derivative of u equals u squared. So for example, if you specify, if you solve this equation with initial data u equals 1 at time 0, you can solve the equation for some time, in fact for time 1, but you blow up at time 1 because this equation has an exact solution. The solution is u of t is 1 over 1 minus t. Okay, so this makes sense for all times less than 1, but as time approaches 1, the solution blows up. Okay, so, this is the exact solution, but one way you can think about this so you can plot u as a function of time. Okay, so at time 0, you start at u has value 1. And so the equation is that the time derivative, the slope, is supposed to be the square. Okay, so over here u has slope 1. So what you expect is that so u is increasing at rate 1. So it will, and you start at 1. So you will soon reach the point 2. And the time that you take to reach the value 2 should be roughly about 1. Your slope is about 1. It's actually a bit less than 1, but roughly about 1. Okay, so your doubling time, the time it takes for u to get from 1 to 2 is about 1. But once u is of size 2, u squared is of size 4. And so now the slope is of size 4, and to double from 2 to 4, if you're increasing at a slope of 4, then to increase it by 2 at a slope of 4, the time it should take to do that should be about 2 over 4, so 1/2. So it takes 1 unit of time to double from here to here, but only a half a unit of time to double from 2 to 4, and until you get from 4 to 8. Okay, now the speed is 16. Okay, you should only take 1/4 of a unit of time to double again. And so what you find with this sort of heuristic analysis is that the doubling times, the time it takes for u to get twice as big as it was before, converge geometrically. And this is why you have finite time blow up. Okay, so this series is convergent, and at the end you have doubled an infinite amount of time, and you have blown up. Okay, so this solution here does not exist globally because the doubling times are converging geometrically to 0. All right. Okay, so in this particular case, you have blow up. But in other cases, you don't have blow up. So many equations, many evolution equations, particularly those that have physical meaning, have some sort of conservation law that stops this sort of blow up, this runaway solution from happening. So often there's some conservation law, such as an energy conservation law, that keeps the energy or some other quantity of your solution finite or bounded, and then you can't actually go to infinity. So, and in particular, if you have some conservation law that traps your solution in some compact set, then this sort of scenario can't happen. So a simple example is that if you have a particle in a potential well, okay, so you can think of, here's space, okay, and you have some potential well, like a hill, and you've got some marble rolling around this potential well. So the equations of motion for a particle in a potential well are given by this equation here, F equals ma. So the acceleration here, dtt of u, is given by the negative gradient of the potential energy. Okay, so this is the equation of motion for a particle in a well. And in this case, there's a conserved energy. The conserved energy is the kinetic energy, the half the square of the velocity, or times mass, but let's normalize mass to be 1, plus the potential energy. And so this is conserved by the flow. Energy is conserved, so the kinetic and potential energy can trade places with each other, but the total of energy is always conserved. So as long as your potential is defocusing, so this potential energy V is said to be defocusing if it goes to infinity at infinity. So it goes up like this. Okay. So as long as V goes to plus infinity at infinity, then the energy conservation law traps U. So if you have a fixed energy, so if the total energy of your particle is of size is E, then your particle can never escape this region here. It must always be trapped inside this interval, and then it can't blow up. Oopsie, that's not what I wanted to do. Okay, so this is a defocusing nonlinearity. So in contrast, if you have a potential which goes to negative infinity at infinity, so this would be a focusing potential, then you can blow up. If you have a marble here, then and if you have a potential that in fact goes, any potential that goes to 0 faster than quadratic, then the more you go out, the faster you become because your potential energy becomes more and more negative, and the situation becomes more like this. You can get finite time blow up. If you have a negative potential, let's say minus x to the 4 or something like that. Okay. So for ODEs at least, the basic story is if you have a conservation law, then which is defocusing in some sense, then you tend to have global solutions. Nothing bad happens. But if you don't have this conservation law, or if your conservation law is focusing in some sense, then your solution can blow up. Okay, so if you don't have this sort of confining, this focusing, so defocusing type of potential. Okay, so that's the story in ODE. ODEs are relatively well understood. So you can ask the same question for PDEs if you have an evolution equation of space and time, and you ask, okay, all right, so sometimes you have global solutions, sometimes you don't. But if you have a conserved energy, and the conserved energy is defocusing in some sense, that the energy surface looks more like this than like this, then okay, is that good enough to prevent finite time blow up? And what's annoying is that the answer here seems to be really complicated. It really depends, and we don't understand completely when it happens, when it doesn't happen. Okay, so just to give you one example, so in PDEs, even having a conservation law doesn't necessarily stop bad things from happening. So just an explicit example is okay. So here's an equation called the focusing quintic nonlinear Schrodinger equation. Okay, so it's an equation of one space and one time dimension. Okay, so it's I dt u plus half dxxu equals this nonlinear function minus absolute value of u to the fourth times u. So u is a complex valued field. Okay, so this is an evolution equation. It turns out to have a conserved mass. Okay, so the mass of this field is defined to be the integral of the square, and this is conserved for all time. And this is a positive quantity, so it traps u in a bounded subset of L2 at least. But nevertheless, this solution, there are solutions to this equation that are completely smooth at time 0, but then they become infinite at some finite later time. So there's an exact solution which you shouldn't really stare too hard at. But it's easier to explain it, to describe what it looks like. Just sketch it. Okay, so the solution. Okay, so at time 0, it looks like it looks kind of like a Gaussian. It's not quite a Gaussian. It's one over the hyperbola cosine square root, but it looks a little bit like a bump like this, and this bump has sort of a width of 1 and a height of 1. Okay, Okay, so it's a nice bump. But as time evolves, what happens? Okay, here's 1. As you approach 1, like for example, if you're just a little bit before on the bad time 1, what happens here actually is that the solution, your solution will push inwards. It will be supported on a narrower interval of size about 2 to the minus n. But it will also become steeper. Okay, it will also become a lot taller. So the closer you get to 1, that means that then 2 to the minus n goes to 0. You get narrower and narrower, but you also get steeper and steeper. Okay, so your wave is focusing to a point. It's getting and then at the final time, it has become sort of this Dirac mass, a little bit like a Dirac delta mass. It becomes discontinuous over here. Okay, so your solution is concentrating all its mass into a single point. So at any given time, the mass is this m of t is always constant. So because the mass is like the integral of u squared. So if u has height 2 to the minus n 2 to the n over 2, you square it. That's like 2 to the n. You integrate on an interval of size 2 to the minus n. That's roughly 1. So the mass stays constant, but still you blow up. Okay. One way of thinking about this is that when you're working in infinite dimensional spaces like L2, the unit ball is no longer compact. So just because you're bounded doesn't mean that you're compactness anymore. Okay, so that's an exact solution. Yeah. So okay, I think I just said all this. Okay. Yeah. So yes, the solution looks takes this shape. Okay. Okay. All right. So all right. So now let's take a slightly different equation. So this is the nonlinear wave equation. So minus dt u plus Laplacian u equals let's say u to the p minus 1 times u. And now we have a scalar field, takes u values, and p is some fixed exponent. This measures of how nonlinear this equation is. Okay. So this equation turns out to have a conserved energy. So much like the particle in a well, it has an energy which has a kinetic energy component, a time derivative. There's a surface tension component, which is coming from the space derivative, and then a potential energy component like this. And the total energy is always conserved. And the basic question is that knowing the energy is conserved, is this enough to show that solutions here exist for all time? So can you blow up? Okay, if you know that the energy is finite. And the answer is it depends. So it depends on this p, exponent p. It turns out that something funny happens at p equals 5. So for p less than 5, if you take this equation for p less than 5, let me just write out the equation again. Turns out that as long as p is less than 5, then the energy conservation law is strong enough to give you global solutions. Nothing bad happens. And that's an old result of Jorgens from 1961. That's for the subcritical case. And then for the critical case, when p equals 5, that was a lot harder. So it took 30 years after Jorgens before we figured out that also for p equals 5, the energy conservation law is strong enough to prevent blow up. And so again, this is a good equation. Solutions exist all the time. But then for p bigger than 5, we don't know. This is okay. It'll take more than 30 years, I think, to settle this question. Okay, yeah, we do not know what happens for p bigger than 5 for this equation. Same thing for the nonlinear Schrodinger equation down here. Again, for p less than 5, we have global solutions for smooth data. This was done again as far back as 1985 by Genebra and Velo. When p equals 5, this was a lot harder. Jean Bourgain was able to prove it in the radio case, and then I managed to prove it in 2008 with 4 other people, Colliander, Kiyosaki, and Takaoka. And p bigger than 5, we don't know. Okay, so right, so where does 5 come from? Okay, we're in 3 dimensions, right? Why 5? Okay, so there is a heuristic that you can use to explain why some PDEs are sort of relatively easy to deal with, and some PDEs are really quite difficult. Ah, okay. Maybe I'll use this equation here. Okay, so yeah, so actually dealing with properly, rigorously with function spaces and so forth can be quite technical, but you can get a handle on how these equations work using heuristics. How come I keep doing this? Okay. All right. So here's your equation. So at any given time, you can pretend. Okay, so at any given point in space and time, your solution should have some amplitude. So it's a wave. Okay, so waves have amplitude and frequency. So at any given point in time, you assume that your wave has a certain amplitude. So it oscillates at some amplitude A, and has some frequency n, which means that its wavelength is like 1 over n. Okay, so let's assume that our solution looks something like this at some region of space and time. Of course, when at different points in space and time, the amplitude may change, frequency may change, but let's ignore that for the time being and just look at amplitude and frequency like this. Okay, so if your solution has amplitude A and frequency n, then when you take the Laplacian here, that's you're differentiating in space twice. So you're dividing by the wavelength twice. So the Laplacian you would expect to be of size n squared times A. Okay, and then over here, this expression here should behave like a to the p. Okay, so that if u is size A, p minus 1 times u should have size by a to the p. And so the heuristic is that so this equation you can think of as a contest between there are two terms here. So the solution is being pushed by two different forces. There's the linear wave equation dynamics coming from surface tension, which is trying to sort of dissipate the wave and push all the oscillation out to infinity, and that's coming from the linear term. And then there's the nonlinear term, which is doing all the bad stuff, focusing your solution together, making it potentially do all kinds of unpleasant things, and that's given by the nonlinear term. And so, depending on which of these expressions is bigger, one of these two terms should dominate. So if the nonlinear size is bigger than the linear size, you should expect some nonlinear behavior, which is bad. Okay, but if the nonlinear size is less than the linear size, you should expect linear behavior. This is the heuristic. Okay. Oops. I always do that. Okay, I know how to do it now. Okay. Back. Okay. All right. On the other hand, if you're in 3 dimensions, okay, so in 3 dimensions, if you have a wavelength of 1 over n, then your solution must spread out. Okay, so it could be localized. It could be localized okay, so your solution, if it has a wavelength of 1 over n, it could be localized to a single ball, or maybe to a slightly larger region. But the region that you are localized to must always be at least as big as the ball of radius 1 over n. This is the uncertainty principle from harmonic analysis. So the size, the volume of your where your solution lives should be at least like 1 over n cubed. Down here. Okay, this is the uncertainty principle. Okay, this is not rigorous, but okay, but it's a good heuristic. Okay, so okay, so you can use this to understand the energy. So remember, the conserved energy here has got a kinetic energy component, a surface tension component, and a potential energy component. And using these sort of heuristics, you can start understanding how big this energy is. So, for example, this surface tension component here so gradient of u is of size n times a, u squared, n of a squared. You've got a volume of n to the minus 3 at least. So the amount of surface tension energy should be at least na squared times n to the minus 3. And then you have a similar bound for the potential energy. And so you have a lower bound for this energy. So if the energy is bounded, energy conservation provides a constraint between the amplitude and the frequency. There is some limit as to how much amplitude you can have for a given frequency. So you do this computation, and then what you find is that this lower bound here, so if your energy is bounded, then this quantity must be bounded. There must be some bound connecting amplitude and frequency. So you have this bound here, and then you can just do a little bit of high school algebra, and you find that if amplitude and frequency are constrained by this bound, then you will be necessarily in the nice linear behavior regime as long as p is at most 5. Okay. Okay, so I'm not going to do the calculation here, but it's just some algebra to get from here to here. And you find that when p is less than 5, you can do this. When p equals 5, you can just barely get from here to here. And when p is bigger than 5, this condition does not imply this condition here. Okay, so that doesn't prove anything, but it does indicate why p equals 5 is important. Okay, and something similar holds for Schrodinger. Okay, so one thing this tells you, one thing this suggests, this computation suggests, is that the worst case, the case that's going to be the most nonlinear, is if all the energy of your solution is concentrated if at each time the energy is concentrated in as small a region as is predicted by the uncertainty principle. So at any given time, the solution may be supported in just a little ball of size 1 over n cubed, or it could be spread out in a more turbulent fashion in a larger space. But if it's spread out in a larger region, then the amplitude will be smaller because of energy conservation, and then you're more likely to be in the linear regime. So the most nonlinear case scenario would be if all your energy at any given time is packed into just one ball of size of radius equal to the wavelength. And if your solution can do that, then, and if p is bigger than 5, if you're in the supercritical regime, then you would expect, then conceivably, blow-up can happen. And this is something we saw. So in this explicit example I gave earlier of the quintic NLS, this is exactly what happened. At any given time, the solution is concentrated in as small a region as is permitted by the uncertainty principle. And so then you actually had blow-up. Okay. So, but what we don't know is whether this actually happens. Okay, so for p bigger than 5, in the supercritical regime, it is potentially possible to have blow-up. At least this this scaling argument does not prohibit it. But we don't actually have a construction that does this. Okay, so I started working on these sort of questions in the last few years, and sort of rather frustratingly, I can't say anything about the actual equations we care about, like this scalar nonlinear wave equation. But I can answer these questions if you allow a cheat. Okay, and the cheat, unfortunately, is a big one. You have to change laws of physics. So for example, for nonlinear wave equations, we don't yet know for this equation what happens when p is bigger than 5. Bigger than 5, do we have global existence or do we have finite blow-up? What happens, we don't know, at least not for the scalar equation. But what I can show is that if p is bigger than 5, then I don't know about the scalar equation, but if you take a vector valued equation, so u takes value in some r to the m, rather than Rn, then there is at least one nonlinear wave equation, so with some potential energy. But I get to pick the potential. There exists a potential energy such that, which is defocusing, so the energy is positive, and it keeps the energy, it keeps all the terms of the energy bounded. But even though the energy stays bounded, the solution still blows up and the potential has the right size. It behaves like u to the p plus 1. But this equation does have solutions which are really nice at time 0, smooth and compactly supported, as nice as you can imagine, but they do blow up. Okay, the solution does concentrate, in fact, to a point and blows up. Okay, so for the scalar equation we don't know yet, but vector valued equations of this type do work as long as m is big enough. Actually, in my proof, m has to be at least 40. So as long as you have at least 40 degrees of freedom, you can force blow up. Okay, and there's something similar for NLS, which is a bit more technical, but I will not mention it here. Okay, so it's a somewhat artificial equation because it involves this potential v that is not natural. It's something that I choose to make the result work. So I would really love to say the same thing for the scalar equation. But it doesn't directly say anything about this equation. But what it does do is that it does provide a barrier to proving. So there are many techniques out there for proving global regularity. And one could hope that one of these techniques, that if you apply them cleverly enough, that you might be able to show global existence for the scalar equation. But now that we have this vector valued nonlinear wave equation for which blowup happens, that tells us that no method can work to prove global regularity for this equation unless it can somehow distinguish the scalar wave equation from the vector value wave equation. And most of the techniques that we know about, if they work for the scalar equation, they also work for the vector value equation. So those techniques cannot possibly solve the scalar equation. If you want to prove global regularity for this equation, you must somehow use some special property of the scalar equation which is not shared by the vector value equation. So it shows that global existence is going to, if it's true, it's going to be very hard to prove. It's going to need a new technique. In fact, I don't believe global existence is true anymore for these equations. Okay, so I want to mention some. Some of the ingredients in the proof. All right. So one nice property of this equation is it has finite speed of propagation. That solutions to this equation. So this is actually a relativistic equation. These solutions cannot propagate faster than speed 1. If you put a c squared here, they would not propagate faster than c. But so the speed of light comes in here, but we normalize the speed of light to be 1. So solutions cannot propagate faster than the speed of light. So because of this, you can actually just work in what's called a backwards light cone. You take time and space, and you take a backwards light cone like this, and you can just specify initial. You can just build a solution only in this light cone. If you can find some nice smooth solution at say time -1, which just concentrates, which blows up. Okay, so it's nice and smooth here, but it becomes more and more infinite as you approach this point here. And you don't bother solving the equation outside here. You only solve the equation inside this cone. If you can make the solution blow up in this cone, then you can extend the solution to the rest of space. You just extend your smooth data however you like outside of this region, and you solve the rest of the equation. But because the solution only propagates at the speed of light, it doesn't matter what you do over here. You won't affect what happens inside this cone. So you can almost compactify the problem by working only in this cone. This basically compactifies space. It doesn't quite compactify time because of this blow-up point here. Okay, so you start to construct solutions in this backwards light cone. Now, there's a standard way to try to construct blow-up solutions which blow up at a point like this, which is to construct what's called a self-similar solution. So there's a certain natural notion of a self-similar solution, which looks like this. So what it means is that the solution at any given time is just a rescaled version of your solution here. So if your solution is doing something over here, it should do the same thing, just scaled. Made smaller, but also made taller. Okay, and it should squash to a point. So you can try so a very standard thing to do is to try just constructing a self-similar solution for this equation. But it turns out, unfortunately, such solutions don't exist. There's a certain integration by parts miracle, which I won't talk about here. But you can show that such solutions will have to have zero energy after lots and lots of integration by parts. But what it turns out to be possible to do is you can construct a solution which is what's called discretely self-similar. So it's not always the same shape, but it keeps returning to the same shape at a periodic set of times. So let's say at time -1, it does something, okay, and then it changes shape, but then at time -1/2, it comes back to the same shape, but rescaled. Okay, so it does something. These are solutions that sometimes called breather solutions. They breathe in and breathe out. So solutions breathes out and then breathes in, and it comes back to where it was before, but smaller and taller. Okay, and then it breathes out again and then breathes in again at time -1/4. It will again have to come back to its original shape, but again narrower and taller than it was before. And it keeps doing this. And then by the time you reach time 0, it will now be concentrated on a set of wavelengths 0 and infinite amplitude, and you get blow up. Okay, so the reason why this is a good type of solution to consider. So one way of thinking about it is that you are quotienting out. So you have this cone, this non-compact cone. So you take the cone, you remove the origin. So this is a non-compact region. But you're imposing a symmetry. And the symmetry is the dilation group by 2. So you dilate by 2, by 4, by 8, by powers of 2. And you're imposing a symmetry of the solution with respect to this group. So if I call this cone gamma, what you're really doing is that you are quotienting this cone by the symmetry group, and you're really solving now a new PDE on the quotient space. Now the quotient space looks like a kind of like a torus. It's what it is. It's a truncated cone. You take the cone from t to the minus 1 to t to the minus 1/2. You take this truncated cone, and then you take this end here and you glue it to this end over here. You take this end of the cone, you squish it down, and you identify it up here. And so you get something that looks like a torus, but a donut, if you wish. Okay, but the point is, it's compact now. You've removed all the non-compactness for your problem, and so you're now trying to solve a certain PDE on a compact domain. Okay, so. All right, so how do you actually solve this equation? So it's so weird. So normally in PDEs, what happens is that you're first given the equation. So you have your equation of motion, your PDE, and then you solve it, okay, to get your solution U. Okay, so you take your PDE, maybe you have some initial data. Yeah, you also have initial data. Okay, and then you solve it to get your solution U, and then once you have your solution, you can start computing various features of your solution, like energy, momentum, various physical features of your solution. It turns out for wave equations, most of the physical properties of your solution are captured by something called the stress energy tensor. Which is a certain quadratic function of your or plus a nonlinear term. Okay, it's a certain combination of derivatives of your solution. Yeah, so it captures both energy and momentum and something called stress. Yeah, so for example, T naught is the energy density, for instance. This thing that we saw before, kinetic energy, surface tension, and potential energy. Okay, and then there are other components of the tensor that measure momentum density and so forth. Okay, so this is an important statistic of your solution. Okay, and it obeys certain properties. So energy is conserved and momentum is conserved, and this leads to the stress energy conservation law. It turns out that this tensor is divergence free, in particular. Okay, and it has some other properties. It's positive definite, and it has some other properties. Okay, so this is a tensor which captures many of the physical features of your solution. Yeah, so normally you start with your equation, you find your solution, and then you compute things like the stress energy tensor. So to construct blowup, we do everything in reverse. What we do is that we first write down a stress energy tensor. So we write down a solution. We write down a tensor which we believe to capture the energy and momentum currents of dynamics of your solution. You first write down a stress energy tensor. It has to obey certain conditions like this conservation law. Once you choose once you guess what your tensor is, you then find a solution U that has that stress energy tensor. So you have to solve this equation here, where T is the data and U is the unknown. And then once you have so the equation I'm trying to solve is this equation here. Okay, so finally, once you have your solution, then whatever it is at time minus 1 is your initial data, and once you have a solution, you then find your PDE. Okay, so once you have a solution U, you find the potential for which this equation is true. So everything goes back in reverse. But this is how you can actually construct solutions that blow up. And it's because I need to choose, it's because I choose my equation last, that's why I don't get to pick my equation in advance. So it's unfortunately, that's the one catch with this method. Yeah. Okay, so maybe some of this is a bit technical. So, but maybe I'll just mention one cool thing. So, getting from the stress energy tensor back to the solution U. Yeah. So it's yeah. So the question is given a tensor T alpha beta, can you find a U which solves this equation? All right. So that's a relatively complicated system of equations, but it is a variant of a much better studied equation. So there's a much more famous system of equations called the isometric embedding problem, where if you start with a tensor G alpha beta and on some compact manifold M, if you want to find some field U such that the alpha derivative of U inner product the beta derivative of U is always equal to G alpha beta. So this system of nonlinear quadratic PDE, this is called the isometric embedding problem. So finding such a U is equivalent to finding an isometric embedding of M into Euclidean space. And it turns out that this equation, this was famously solved by John Nash in the 50s. So he proved the Nash embedding theorem that given any smooth compact manifold of a certain dimension, if you make this dimension M big enough, you can always embed any fixed dimensional manifold into Rm isometrically. But the dimension has to be pretty big, and so this is why I need 4D dimensions. So actually, there's a 4-dimensional manifold that I need to embed isometrically into a certain space, yeah. So I think Nash needs like 16 or 17 dimensions to embed a 4D manifold. For this more complicated problem, I need 40 dimensions. But yeah, so very conveniently for me that this problem was already solved by this Nash embedding theorem, and that lets me get from here back up to here. Getting from the solution U back up to the equation V to find V, this is actually not too hard. This uses classical analysis, in particular the T extension theorem is the main tool. Yeah, so the most tricky thing is actually to find a good stress energy tensor for which everything else works. Yeah, so the stress energy tensor has to obey a certain number of conditions, but it turns out that in 3 dimensions at least, you can make a lot of symmetry assumptions. You assume that your stress energy tensor is rotation invariant and dilation invariant, and after making a lot of symmetry reductions, the conditions that you need boil down to solving just a whole bunch of a small number of ODEs. And you can actually just solve the ODEs by hand explicitly. And you can find a stress energy tensor that does what you want. Actually, what happens is that the energy tensor actually concentrates very near the boundary of this cone. So it's like, the solution becomes like an imploding shell. It's a shell of energy that implodes to a point. Okay. All right, so that's all I'll say about the wave equation. Let's just see what I am doing with time. Ooh, yeah, okay. I think I'll skip Euler and just talk about Navier-Stokes because okay. So yeah, so the equation that I most care about, which but I can't resolve, no one can resolve, is the Navier-Stokes equations. Okay, so we go back to the okay, so the fluid equations for water. So this is an equation for studying fluids with both viscosity and pressure. Pressure is a bit annoying, so it turns out that you can eliminate pressure from this system. There's a singular integral called the ray projection. It's the orthogonal projection to divergence-free vector fields. This is a gradient. Gradients are always orthogonal to divergence-free vector fields. So if you project to divergence-free vector fields, you can eliminate the pressure, and you get instead you can turn the Navier-Stokes equation into a nonlinear heat equation. So you can simplify the system to just dTu equals viscosity plus U. That would just be the heat equation plus this annoying bilinear nonlinearity, which is this somewhat complicated bilinear multiplier here. Okay, so this bilinear multiplier has a certain property. There's a certain cancellation. This BUU is always orthogonal to U, as it turns out. So this you can check by an integration by parts. And what that means, it's equivalent to energy being conserved, or actually energy being dissipated. So this equation, it doesn't quite conserve energy because of the viscosity. Viscosity will drain away energy, turn the kinetic energy into heat. But what you find is that the kinetic energy of your fluid is always decreasing okay, and it's always dissipated as heat. Okay, so in particular, this energy is always bounded in time. And in 1 and 2 dimensions, that's enough to get global regularity. So the Navier-Stokes equation is subcritical in 1D and critical in 2D, and that's good enough to get global regularity in these dimensions. But the dimension we care most about is 3 dimensions. And in 3 dimensions, unfortunately, this is a supercritical equation. The energy conservation does not prohibit the solution from being in the nonlinear regime, where the amplitude is so big. So the amplitude can be so big, potentially, that the nonlinear behavior happens. So it does not seem that the energy density is strong enough to prevent blowup. And the big question is does the Navier-Stokes equation actually blow up? Right? There's a $1 million prize for anyone who can prove that or disprove that. So I can't do it. No one else has said. But what I was able to show about 2 years ago was a similar sort of cheat to before. If you change the laws of physics, then you can answer the question. So if you take this equation, but you replace the actual nonlinearity BUU, which captures the physical features of the Navier-Stokes equation, by what I call an average version of BUU, so something a little bit smaller. So it is possible to make the nonlinear term a little bit smaller by averaging it against with respect to certain symmetries. But let me not talk exactly what averaging means. It's a bit complicated. Then there exists an averaged equation which still has good energy property. It still obeys the energy inequality. So energy is still dissipated, but now there are solutions which start off smooth and very, very nice, Schwartz class, but which blow up in finite time, which concentrate to a point, much like these other solutions here. They're not quite self-similar, but they're close to self-similar. And so I wasn't the first to do things like this. There's previous work of Montgomery Smith, Shaman, Gallagher, Paiku, and Lisa and I, but the previous equations that constructions did not have energy conservation. So the energy was blowing up together with the solution. But this is an example where the energy stays the energy is still bounded, but the solution blows up. So what this tells you is that you cannot solve the Navier-Stokes equation regularity problem just using the energy conservation law and standard methods. You would need to use some technique that distinguishes the true Navier-Stokes equation from this sort of fake Navier-Stokes equation here. Okay. Yeah, okay. All right. So I just maybe say a little bit, I'm running out of time, a little bit about what we do here. So it's a similar sort of, yeah, so I don't construct these self-similar solutions. In fact, I don't even know if they exist for Navier-Stokes. Yeah, but the idea, again, is to create something like a discretely self-similar solution. So a solution which at a given time is localized to a certain region of space and has a certain frequency and a certain amplitude. And then it does something, it breathes, it goes in and out and does something. Okay. But after a certain amount of time, you want it to concentrate into an even smaller region of space and with a higher amplitude. And then it will then breathe out and breathe in again, but faster now. Okay, so that maybe in half the time it will concentrate, it will rescale to a smaller version of itself, and then do that again and again and again until you blow up. So you can sort of manually choose a nonlinearity to sort of push. You keep trying to push your solution into smaller and smaller scales. But when we and I wasn't the first to try doing this, but when you do this, when you try this in the most naive fashion, you encounter a phenomenon known as Kolmogorov turbulence. So when you actually take actual fluids, fluids don't do this. Okay, if you make a little eddy of water, this eddy of water does not spin into a smaller eddy of water and then spin it into an even smaller eddy of water, and so forth. What happens is that the energy spreads out. So maybe some of the energy will move to this smaller scale, but then the energy here might then, while you're trying to squash this energy from this scale to this scale, the energy at this scale is itself pushing energy into an even smaller scale, and so on and so forth. And what will soon happen is that your energy of your fluid will spread out in a power spectrum. There'll be some portion of energy at low frequencies, some at medium frequencies, some at high frequencies. And once you have enough energy spreading out, then the amplitude drops to a point where the linear term dominates again. So you cannot stay. It turns out you don't stay in the nonlinear domination regime if the energy can spread out. And so the hard part of this work was that I had to somehow program this nonlinearity. I choose this nonlinearity to prevent the Kolmogorov turbulence effect from happening. So what I had to do was I had to keep the solution localized at one region of space, one frequency, and you keep it there for a certain period of time, and then you very suddenly squash it to the next higher. So the solution sort of spins on very slowly at a certain frequency, and then it suddenly collapses to something of half the size. But then you have to make a stop again. You have to, so you then have to sort of put a delay in your equation, so you have to wait for all the energy from the previous mode to drain into your new mode before you start the next phase of the cycle. If you have all these sort of energy transfer modes going on simultaneously, you get this turbulence effect. So you have to sort of program your equation almost like making a circuit, actually, like designing a circuit. And so actually I got this idea from my wife, actually, who was trained as an electrical engineer. And engineering is somewhat the opposite of mathematics in some sense. In mathematical PD, you're given the equation and you start solving it. But engineering, you have a desired outcome, a solution, and you want to design your circuit, just design your equation that will produce the given output. So it's sort of the opposite mentality. And engineers design circuits, out of simpler objects, like maybe capacitors and resistors and so forth. And you take these simpler objects and you put them together. And so I had to make these. So I built this nonlinearity, which is rather complicated, out of smaller, simpler nonlinearities which behave kind of like actually like logic gates and in OR gates, and I had to program a simple clock so that your solution only moves from one frequency to another after a certain time delay. But anyway, it is possible to do this after quite a lot of work, and you can create a rather weird equation which behaves like Navier-Stokes and blows up. So as I said, what this tells you is that this rules out, so many of the existing techniques to prove global regularity will not work to solve Navier-Stokes because they cannot distinguish the Navier-Stokes equation from this artificial average Navier-Stokes equation, which does have finite time blowup. So if you want to solve the global regularity problem for Navier-Stokes, which I don't believe is true actually, but if you want to do it, you must use some property of Navier-Stokes which is not true for this average equation. Now, there are such things. Okay, so this result doesn't exclude every single possible way to prove regularity for Navier-Stokes. For example, you can take the curl of the Navier-Stokes equation, and there's an extra equation which is very important for Navier-Stokes, which is something called the vorticity equation. So there's something called the vorticity, which is the curl of the velocity field. It measures so how much your fluid spins, and this obeys an additional equation in Navier-Stokes. But this average Navier-Stokes equation does not obey an equation of this form. So one possible loophole here is that if you want to prove global regularity for Navier-Stokes, you would somehow need to use this equation. Now, I do believe that there is some modification of my construction. There should be some way to construct an average Navier-Stokes equation that also obeys the vorticity equation and which has finite time blowup, which would close this loophole. I can't do that for Navier-Stokes. I can do it for the Euler equations, but I think in the interest of time, I will not discuss those results. And I think I'll just skip all that and finish. Okay, thank you.